Hi, Joe.
Hello.
And your dad. Apparently, your dad is helping today instead of your mommy with any experiments that we get a chance to do. Fantastic. So today we're moving on to physics. As you know, physics is one of the sciences. And yesterday you decided that you wanted to do Newton's laws of motion. And we have already introduced who Isaac Newton is, so we don't need to do that today. And we'll start by looking at the 3 laws of motion.
Okay.
Do you know any of them? Have you ever heard of them?
Force.
Hmm?
Force.
Yeah? What about force?
That an object cannot move.
Yeah. Yeah, I'm just writing. That, you said force, and what did you say?
That an object cannot move without force.
Yeah. So it says an object cannot move without force.
Yes.
Anything else that you know?
That's the only one I know.
Okay. So essentially what you know is yes.
Wait. Quick question. Is gravity something, or is it something else?
Yeah, there is the law of gravity that Newton, which is something that Newton discovered, but it does not form part of Newton's laws of motion. However, gravity does play a part in everything remaining in balance, because remember, gravity pulls things down. For example, if you were to think about it, if you're in space, what do you know about space?
In space, there's no gravity, so let's say that you're in space, you try to you just float away.
Yeah, and if you threw something, what happens to the thing?
It would just float.
Yeah.
And I also know that if you were to squirt, so let's say you have a juice pack and you squirted it in space.
Yeah.
It would bubble into a bubble.
Yeah.
For some reason.
Yeah. And that bubble will just float because but for example, let's say you today threw something or squirted that bubble out of the juice packet that you were drinking. What would happen?
It would turn into a bubble and float away.
But no, if you did it here on Earth.
Oh no! Then it would just be in kind of like it would be like an arch of juice just going out of the pack.
And what happens as it goes out of the pack?
It falls. It falls.
Yeah, and splatters all over, drops everywhere and splatters all over the ground, isn't it?
Yes, but in space, there's no gravity.
Yeah. Yes, at times the video sort of freezes and I miss some of the things, but don't worry. So you said in space there's no gravity, so the juice will just float around as a bubble, and on Earth it will just literally drop to the ground. So that already tells us that gravity is a force that does what?
That keeps objects on the ground.
Yeah, so gravity is a force that keeps objects on.
And people.
Hmm?
And
Yeah, that keeps objects and people, like you say.
wait, so.
Yeah.
So okay, so how come on Earth there's just enough gravity for us to still be able to move?
Yeah, which is why we're going to focus on Newton's laws of motion. All your questions can be answered using Newton's laws. For example, the Newton's third law of motion tells us that, when we get to it, that for every force there is an equal but opposite force. So if you wanted to move, you have to overcome a force that's pulling you down and push against it. But if you are pushing against it with an equal force, for example, like when I'm standing here, I'm just pushing against the ground with an equal force that the ground is pushing up against me. But if I want to get away from the ground, for example, if I want to run, if I want to jump, I have to absolutely push against the ground and then I can jump up. Do you understand?
Yes.
So that's how people can overcome forces like gravity that are wanting to pull them back. You have to exert a much greater force that overcomes the force that's actually pulling you down. Does that make sense?
That makes sense.
Fantastic. So shall we start with the first law of motion? So actually you already have a good idea of, what Newton's laws of motion are. And yes, Joe?
No, I was trying to see whether the thing I said is actually true and you can move an object with force.
Yes, we're going to do that because it could be helpful for us to first of all understand what the laws are and then do the experiments to demonstrate what the laws do, such as what we did with the digestive system. Remember, we first of all learned what enzymes are, and then we also learned what test buds are, and then we did experiments that demonstrate how things work. Right? Yeah. So Newton's first law of motion, we'll call it, I'll just write one so that we can save space, but because if I write Newton's first law of motion, it will be a long sentence, but you know that this means Newton's first law of motion, right?
Yes.
Yes.
It's because you already put heading or subheading.
Yes. So it says an object, an object that's just standing still there will remain in that position unless if another force that is unbalanced does something to cause it to be displaced, i.e. to move about. And if an object is already moving in one direction, for example, say if an object is walking away from the board while walking parallel to the board, that object, I can't see, you've paused the camera, that object will continue walking in that straight line at the same speed. You understand what speed is? Yeah, at the same speed, and it will not change unless if an outside force that is unbalanced causes it to either turn and change direction or move faster. Does that make sense?
Yes.
So Newton, yeah, go on.
Wait, okay, so let's say that the thing that was staying still
Yeah.
is the car.
Yeah.
And then someone makes the car move,
Yeah.
moving at the same speed in the same direction that it was facing.
Yeah.
So then I'm thinking of a way to put it.
You're thinking of a way to
Put it.
put it. Perhaps a car might not be the best way of thinking about things because a car involves a lot of mechanics. But if you think of the wheel of a car itself, right? It rotates. Well, obviously, if a car is standing, in motion and you parked it, the wheels are not rotating. They are not moving at all. Once you start the car and it starts moving, the wheels start rotating. And as they are rotating, they are pushing against the ground. And if you accelerate a bit more, you are increasing the force that the wheels are pushing against the ground, and they spin a little bit faster, and the ground pushes against the wheels and causes things to move forward. Or if you had your own toy car, which you know you've played around with toy cars, I don't know whether you still play around with them. And if you left your toy car on your study desk, sitting there, it will just sit there. However, if you tap it a little bit, it will move forward. If you pushed it a bit harder, it moves forward but faster. If you took, say, this pen and sort of edged it to the side and then continue pushing it, it will turn direction and move towards the direction that you want it to go, right? But remember, on Earth, there are things like friction, which then, yeah.
When you were saying that the wheels would rotate against the ground,
yeah. So yeah, absolutely. There are things like friction which are resisting what you are trying to do, and then that causes things to eventually slow down. But if you were in space where there is no friction, where there is no gravity, things will just continue on, same speed, same direction. And so Newton's law of motion must always be compared with space in order for you to think about things in a more clear way. And then when you introduce friction, you can then understand how you overcome forces.
Okay.
And when you introduce gravity as well. So Newton's law of motion, the first one is called the law of inertia. We can call it like that. Do you want to look up the word inertia in your science dictionary and also in your Oxford English dictionary?
Okay, first I'll check that. Okay, so how do you spell it?
There, can you see it?
ABC. Ah. So in it's not that.
It's not there. So it's INERTIA.
Okay, now I'm checking the dictionary.
Which one are you now using? Okay, Oxford School Dictionary.
Found it.
Yes. What does the word inertia mean?
Being unwilling to move or take action, or two in science, the tendency for a moving thing to keep moving in a straight line.
Yes. So now do you feel you have a little bit of understanding? Can you give your dad your science dictionary and see whether he can find laws of motion, or whether he can find a way of defining inertia in the science dictionary? Then we can move on. That will be part of your homework to read up on it, but it would be good if the science dictionary already had more scientific explanations. So that's what inertia is. So it's the tendency for objects to remain in that same position. For example, you showed me a sweet that is wrapped in a paper. Yes. If you were to put it on top of your study desk there, what's happening?
Nothing's moved. It's not moving.
Yeah, it's just sitting there, isn't it?
Yeah.
You have a marble, haven't you? Do you have a marble in front of you on your desk?
Marble somewhere.
Or a small ball, anything really?
Here's a marble.
Oh, fantastic. So, if you were to roll the marble on your desk...
It's okay. I just placed it on the desk, but
No, but I roll it.
it's moving.
Yeah, so it keeps moving, doesn't it? Until it either falls or something on the desk blocks its motion and it stops. What stopped it?
This hand that has this.
All right. So yeah, all your things. So yeah. So that's what happens in terms of Newton's laws. That something will continue on until an external force causes, it to become unbalanced by either blocking its path or propelling it forward to move faster or causing it to change direction.
Like this pen, I could use this pen to make it change direction.
Yeah, why don't you do that? So if you were to put your marble down and then use the pen to cause it to change direction.
Yeah, it did. It changed direction.
Yeah, so that's what Newton's first law of motion says. It's if you think about it as the inertia. If you remember the definition of inertia, then you can be able to define Newton's law of motion. Can you tell me what your understanding of the first law of motion is?
That if you were to place an object on a surface, any surface, the object would not move.
Mm-hmm.
But if you were, let's say, to push it
Mm-hmm.
against it, it will keep on moving.
Mm-hmm.
It hits an external object.
Mm-hmm.
It will make the force unbalanced.
Mm-hmm. So unbalancing that force of movement could either be stopping it.
Yeah, they could stop it, make it change direction, or make it go faster.
Yeah, or go slower.
Or go slower.
Yeah, fantastic. So you have a good understanding of it. And then we move on to Newton's second law of motion. So Newton's second law of motion is about things moving, accelerating. Do you understand what the word accelerate means?
I know what accelerate means.
Yeah.
But
So we call it the law of acceleration. And what it means is that we now think about objects in terms of, this object is still perhaps, we always start at the starting point, which is standing still, not moving, not doing anything. So we think about the object and think, gosh, this object is just sitting there, For it to accelerate and move forward, what can we do? We've already touched on this already. What did we say? Do you remember?
and you can push it.
Yeah. But in order for you to then cause it to move forward, what do you think when you are pushing it you must do? What sort of force do you need? A smaller, bigger?
To make it move forward.
Yeah.
How far you want it to go.
Yeah.
Because if you wanted it to go a short distance, then you just push it slightly.
Yeah.
And a short distance. But if you wanted it to go a long distance.
But just stop playing with the thing because it's making I can't hear you. It's making more noise than your voice, higher level of noise than your voice. So what did you say?
I said that it depends what distance you want the object to cover, because if you wanted it to go a short distance, you would only push it slightly.
Yeah.
To go a long distance, you would push it with more force.
Fantastic. However, for it to actually start moving, do you think you need, a smaller force or any force at all, or do you think it can just, what do you think?
I will need a force to move it.
Okay, so the way we determine the amount of force that is required is we think about how much does an object weigh. Does that make sense?
Yes.
So Newton's second law of motion brings in, so F is force that we need to push something. So we'll write the word force. The force that we need depends on how much an object weighs, and you know that weight is mass of an object. Do you?
Yes.
Fantastic. So mass multiplied by by acceleration, like you said, how far you want it to go in terms of the starting point as well as So then, in order to think about forces that result in acceleration, you then have to think about how much things weigh. So how much things weigh actually decide how much force you need. For example, you have a marble in front of you, and do you have what else do you have in front of you that's circular?
Circular. I have a peach.
Okay, so between which of the two has a larger weight?
This one.
Okay, so if you wanted both the peach and the marble to roll across your desk, what do you think? Do you think you have to push them with the same amount of force, or do you think one of them requires a little bit more force to overcome inertia?
I think it might need a greater amount of force.
What needs a greater amount of force? I don't know. Which one? Sorry, which one?
The peach.
Yes, why do you think the peach needs a greater amount of force?
Because it weighs more than the marble.
Okay, and if we think about the first law, you remember we said in order for things to move, you need the force to be unbalanced, isn't it? So in order to overcome the weight of that peach, which weighs a lot more than the marble, you need to exert more force that will then cause its inertia to be unbalanced, and then it will move forward. Does that make sense?
Yes.
Okay, tell me in your own understanding.
That's an object as greater weight. We'll need a greater amount of force for it to be pushed against it for it to move.
Fantastic, yeah? And really, that is Newton's second law of motion. We start to think about what does the object weigh? How far do we want this object to move? And once we have determined those things, we then know the amount of force that we need in order to push those things forward for them to start to move. So we think about, first of all, the first law. Well, this thing is sitting there. It doesn't want to move, and it will never move unless we do something to unbalance its forces, because as it's sitting there, there is a force that's just keeping it there. So in order for us to unbalance that force and cause it to move, we must push it forward. But oh gosh, how much force do we then need in order for us to push it forward? Because your dad is there with you. If you weigh different, yeah, your weights are different. So if there was a wind, if it was really windy outside and you were walking with your dad in the park, there were no trees, there was nothing, the two of you were just taking a lovely stroll, and then suddenly a gush of wind comes and pushes both of you, obviously. What do you think will happen?
this is actually happened once.
Oh, has it? So tell me what happened.
Not actually at the park, but we were just walking.
Yeah. Yeah.
Then there was a really, really strong wind.
Yeah.
And it was pushing against us.
Mm-hmm.
Gabby was still able to walk.
Yeah.
I was just standing there, barely able to move, but I could still move.
Yeah.
It didn't push me back too hard, but if it was even stronger,
yeah,
it would be pushed back.
Okay, so the wind was pushing against you. It wasn't a wind from the back.
It was a wind from the front.
From the front, yeah. So your dad, because of his weight, he was able, so you can tell that the force of the wind was perhaps greater or equal to your weight, but it was smaller than your dad's weight, which is why he was able to overcome the force and keep moving forward. However, say if that force was coming from the back, what do you think would have happened?
Would it have made me move forward?
Yeah, but what about your dad? As you are moving forward, remember we're thinking about the two of you walking side by side. A gush of wind, strong force, pushes you forward, both of you. What happens to your dad?
It pushes both of us forward.
Yeah, but what happens? Does it mean that you are both walking forward, you keep walking side by side like this, or does one of you get pushed forward a bit more and it literally run while the other person is still able to walk?
Oh, one person would start running.
Who will start running?
Me.
And why do you think you will start running?
Because the wind, as it has a greater force than my weight.
Yeah.
It would be pushing me forward faster than I was walking. So.
Absolutely. So, yeah.
The wind is now. This is me.
Yeah.
This is Dad.
Yeah.
Side by side.
Yeah.
Then all of a sudden a wind comes from the back. I'm like, ah.
Yep.
Still walking.
Yeah. And your dad might not even feel the wind. He might think, why is my son running forward while he's still standing still? And you'll be like, Dad, there is this wind, which is a great force that's propelling me forward. So now it shows us that, in order to unbalance something, because think about it, the wind has already caused you to be unbalanced. You are literally running without really wanting to run. The force of the wind is causing you to run forward. Yeah. And your dad is just standing there and thinking, there is no force here. Why is my son suddenly running away from me? So does that make sense? So your dad will still be, either standing still in inertia or still walking at the same speed that he was walking, remember? Which still is inertia because he's not unbalanced in any way. So he continues on and you running. Yeah. So that is another way of thinking about law of acceleration. Sadly, we have 5 minutes. Shall we leave it there, or do you want me to introduce the third law quickly? Do you feel you have a good understanding of the first and second laws?
Yeah.
Do you want me to introduce the second law, or do you want to stop there? To introduce the third law. There are only 3.
Okay, we can stop there.
Okay.
I was hoping we'd be able to do this again.
Okay, yeah. Well, as part of your homework, I would like you to think about things and think about the forces that are required and to actually, experiment. And even now, perhaps if you can start if you, what else do you have in front of you?
So I have the sweet, the
Yeah.
marble, an easy peel, a peach, an onion, and a potato.
Okay, so if you were to pick up, what's
Also
that?
the stock,
Oh, okay, yeah.
the bag.
Okay, so if you were to pick up perhaps an easy peel and a potato, yeah, and you probably need the ground. And if you stand and kneel down perhaps as a starting point and push them both using the same force, let me know what happens. You want to do that now? Yeah. Same force. What happened?
Still haven't even done it. Same force. The potato didn't move.
So the potato didn't move at all.
Yeah, the orange is moving.
Okay. So now I want you to increase the force on both, but it must still be the same force, but a little bit harder than you did.
Okay, the potato moves a little bit.
Okay. So you are still, can you see that you are still trying to overcome the force of the potato? And then now think about how far you want the potato to go. And then apply that exact amount of force. But remember, you are only thinking about the potato, how far you want the potato to go. But apply the same force as though both the potato and the easy peel were the same.
I thought how far I wanted the potato to go.
Yeah.
It went as far as I wanted it to go.
And what happened to the easy peel? Because I said both of them at the same time, but thinking about how far you want the potato to go.
I don't know why, but for some reason the easy peel just stopped.
Just stopped.
Yeah, it just stopped.
Okay, but did it go further or a short distance?
It went a short distance.
Okay, normally because the easy peel weighs less, what would you have expected it to do if you applied the same forces you are applying?
I would expect it to go ahead.
Yeah. Was there anything stopping the easy peel? Was there anything in its way?
Oh, it was that's foot.
Wow. So we have an external force that's unbalancing it, isn't it?
Wow. I put it with the same force. That one's way ahead. Of course, the potato hit against the orange.
Oh, right. So perhaps you need to do it where there is a bit more space on the ground.
Okay.
Joe? Joe?
Yes.
Okay, so perhaps that's what I need you to go away and think about and do. Did you manage to do it now or not? Not quite. Okay, so yeah, you need to look for a place where there is nothing and then push both. However, for today,